Hi, my name is Adam Weller, and today I'm going to share some findings that we've had on how to identify applications using network metadata. I've been at Cisco for 8 years. Currently, I'm on the threat intel team in our incident response organization. I know that Cisco's a large company, and I get a bunch of questions in terms of where that means I am. So this is separate from our customer-focused threat intel, that's Talos, and this is also different from our product security team in CSIRT. Let's talk about what we're going to cover today. I'm going to start with a simple use case talking about passive DNS and how we can monitor for that. Next, we'll look at how we can combine endpoint and network metadata. And then we'll look at how we can support incident response use cases. Lastly, we'll walk through a case study showing how we detected previously undetected malicious activity. Endpoints can have monitoring agents disabled by malware. Not all of your devices on your network may even support endpoint monitoring. Think about cameras, badge readers, internet-connected refrigerators. Your company might also support a BYOD model, in which case devices won't likely report to your corporate AV instance. They might also not use your corporate sanctioned DNS provider. Let's start by digging into how to monitor DNS traffic observed by monitoring network activity. A simple question, what is passive DNS? Passive DNS is the storage of DNS requests. You can think of this as a ledger of who requested which domain and when. You might even be a passive DNS question on the capture the flag in case you're participating on that competition. This is different from getting logs from your active DNS provider. While your active DNS provider can give you some added security in terms of blocking domains, it's not comprehensive, as we'll talk about more. There are options for how much data you have to store. You can store just the requests, which has a lot of value, or you can store the questions and the answers. A few quick reasons about why you should believe in the value of DNS monitoring if you don't already. A sysadmin sets up a server in the lab. Do they always set it up to your corporate DNS? Do they know better than your IR or your InfoSec team? Do they set it up for Quad 1, Quad 8, Quad 9? I see some nodding. People have experienced this. If they do that, capturing the logs only from your DNS provider might not be enough to catch this activity. This data is super small and readily compressible. Given the small size, it's possible to save that data for quite some time. Keeping that data for months to years is essential to investigating malicious cyber activity. Often activity is not discovered and shared for months, so being able to go back and look at that historical data may be your only way to find bad actors. Larger volume logs may have aged out of your SIM, so that retaining the compressed metadata might be your only option. For many of us in incident response, SolarWinds will be remembered as the incident that dominated the 2020 end-of-year shutdown or holiday period. For those of you who don't remember it, it was a supply chain compromise. The actor gained access to the code base and was able to modify shipping binaries to customers. While the reporting was published in December, some of the activity called out in the report was from June and July of 2020. However, the compromised binaries date back even months earlier. One of the interesting things about the compromised binaries is that they called out to command and control domains that determined whether or not to deploy second stage malware. So when your CSO asks, were we impacted by SolarWinds, it's important that you can answer the question definitively. Monitoring DNS requests is a great way to do this. Okay, now let's get down to the nitty-gritty. Starting at the left of the diagram, this is a simplification of all of the endpoints on your network, the laptops, the servers, everything that you have. The network tap is shown by that yellow arrow, where things might get a little bit more interesting. This can be an Ixia, a Gigamon, a Nexus data broker. It could even be a magical PCAP fairy who hands you a never-ending series of USB drives. But for the purpose of this, we'll focus on data brokers and the continuous data flow. The data is allowed to travel to the internet without blocking. A copy of the data is sent to our open source software, Mercury. Mercury was developed at Cisco with the goal of capturing useful metadata from encrypted traffic. It was a rewrite of previous tools written by the team. So yes, there's a zero-copy ring buffer. We can scale to high-speed links with a modern AF packet fanout, but this is not the talk for the internal guts of Mercury. This is the talk about looking at data and how we can use data for incident response. From Mercury, we can copy the data to our Spark and HDFS cluster. At this point, I'm sure that some of the engineers in the room are wondering just how expensive it is to run Mercury. There are 3 basic options in terms of link speeds that you can support. So you can look at it from UDP 53, or basically just DNS traffic only. And that can be 2 virtual CPUs and 8 gigs of memory. You can monitor a full span link at 10 gigs for 8 virtual CPUs and 64 gigs of memory. If you want to monitor a 40 gig link, that's roughly quadruple, so 32 virtual CPUs and 96 gigs of memory. This is a little bit flexible in terms of how your deployment looks. So if you have more compute at your ISP gateway, you can do the processing and compression there. If you have more bandwidth than compute, you can bring your data back to your large data cluster and handle your compute and processing there. Here you can see the size for roughly 1 million requests and the different data schema options. The first is for the full JSON objects from Mercury. If you're only interested in DNS, you can limit that and cut the file size down by more than an order of magnitude. This uncompressed size is also important to consider if you're looking to send this data to your SIM like Splunk, since the uncompressed data size is what you're going to be ingesting there. The smallest file size is at the bottom, the Parquet file. This is the compressed file that we're storing on HDFS. The smaller file size doesn't just make it easier to retain more data, but it also means that you can stream the data off the disk faster to process in Spark. Now that we've covered monitoring DNS activity on the network, let's talk about how to combine network and endpoint data to identify applications. I know that there's a lot going on here, but I can unpack it step by step. First, at the top left, you have all of your endpoints that have been shown previously. I removed the cloud, sorry cloud people, but know that these devices are still connected to the internet. The endpoint traffic flows through Mercury just as it did before, and from Mercury it goes to the big data cluster. All of that's the same. However, there are 3 additional data feeds. First, we have data from malware executed in our threat grid sandboxes. This provides useful PCAP generated when the malware ran. Second, our repository of malicious IOCs lives in threat queue. This can be domains, IPs, it can even be user agent, whatever you have. The last data feed is on the left and comes in from the endpoints. This is our network visibility module feed. This comes installed on our corporately managed devices as part of our AnyConnect software. If you have something different in your environment, you could substitute that here. Think of it as a way to get ground truth about a binary running on a managed host. All of these data sources flow into our centralized big data cluster. Once the network and endpoint data is in the big data cluster, a nightly data fusion pipeline can execute. I'll talk more about that in just a few minutes. The next step may be a bit triggering for some people who who have some buzzword issues, right? So if you're like my boss and have really strong disdain for machine learning, and I want to point out this is in 2018, so this is back when AI meant PowerPoint and ML meant Python code before large language models. Sorry, Mike. So if it makes you feel better, we can make that simple change in terms of a classifier. And for the people who asked, yeah, the classifier is an automated processing. It's not just keeping interns trapped in a conference room for the summer. So once you have the classifier determines which events are of interest, we can then take those records and send them to our SIM. Once in the SIM, our existing automated playbook is able to fire on the events and create new cases. Now, let's talk a little bit more about the data fusion. We can start by looking at a portion of the TLS connection that's not encrypted. This can give you quite a bit of information about the client requesting the connection. All of this information that you're putting together, the protocol version, the cipher suites, the extensions, all of that starts to form a pattern. From that TLS client hello, it's possible to construct a fingerprint. This fingerprint can be broken down into a number of sections that I show here. First, there's the protocol. In this case, we're looking at TLS. There's also fingerprints for other protocols like QUIC or TCP. Next comes the version, and that's followed by the cipher suites. It's important to note here that the fingerprint is most commonly used in the text representation. For the case of cipher suites, what that means is it allows you to get near matches. For example, when a browser adds or removes a cipher suite, you're going to have a small change. This is different from hashed representations of fingerprints because in that hashed representation, when any of this changes, there's not the possibility of tracking that near neighbor. Now, if we look at the larger record for Mercury, you can see the TLS fingerprint that we talked about on the last slide. In addition, there's some super useful metadata. Source, destination IP, source, destination port, along with the protocol. There's also a timestamp, which is super useful when looking at other data. Now, the NVM data. As you can see, it has the 5-tuple that we saw previously. There's also information about the process. The hash, the name, the arguments, information about what launched the process. You could substitute what you might have from another endpoint monitoring agent, but NVM is the data that we have, and it's extremely useful for us. So when we talk about the fused record, it's the combination of the Mercury record and the NVM record where we join on the 5-tuple and the timestamp. For those of you who are paying attention at the back, you might have thought, if you already have the data from the endpoint, what else do you need? Isn't that everything? Isn't this solved? You think you have the metadata to make the conviction, so why do I need this? I can feed that into my automated playbook. However, oftentimes your real operating environment is a bit messier than this ideal case. Maybe not all of your devices are managed. Maybe some of your users have local admin and they disable endpoint collection because they know better than the InfoSec team. There is an option. We recommend that everyone build a fingerprint database for traffic on their own network. All networks are different. Some have Windows laptops, some are Mac first with Windows by exception. You may even have Chromebooks with rigid application whitelisting. If you have an on-site data center or a lab environment, that may add even more diversity, Red Hat, Ubuntu, containers. There's also a variety of applications that might be geographically distinct to 1 or 2 regions. For our network, we have over 3,000 TLS fingerprints, over 3,500 HTTP fingerprints, and 125 quick fingerprints. If you look at the fingerprint at the bottom of the slide, you can see that this is another example of a TLS fingerprint. For this example, the fingerprint is associated with apps like Office. You'll notice that I said Office and not Word or PowerPoint because they use a common code base to make network connections, so you can't distinguish between them. Additionally, you can see that there are other applications like iTunes that generate traffic with the same fingerprint. In this case, if you saw this traffic on your network, most likely it's going to be benign. But you can look into it a little bit more. You can also process PCAP from malware samples executed in sandboxes to identify suspicious or malicious fingerprints. Before, when we talked about our nightly pipeline, we talked about sending events of interest to our SIM. The question is, how do we identify which events to send? For example, we can determine to only send fused events that contain both network and endpoint data. Alternatively, you could send events based only on the network. Given the additional context of the fused record, it's much easier to resolve cases. However, with additional analysis, you may be able to do that attribution to get something to resolution with only network data. You could also determine that you want to handle the two sets of cases differently. Maybe you want to send a fused record to tier 1, possibly leading to a device reimage, whereas for the network-only data, maybe you want to send that to tier 2 or tier 3 to have them go through more analytical steps to find out whether or not the traffic is malicious. Let's look at an example of how we can use some of this to see what an application is and whether or not it might be malicious. Here we see that there was an event identified by our nightly processing pipeline. In this case, suspicious activity from something purporting to be Duo device health. On our network, we use Duo for MFA and Duo device health for posture enforcement. So it's certainly likely that Duo device health could be running on our network. When I look at the 3 domains in our threat queue instance, here's what I get. I get one with no results found. I get one that's an expired indicator. I get one with a very low score that was actually whitelisted. In this case, you have 3 very different outcomes, and you can imagine that for your case, you may have only one of those 3. So it seems like we're not going to get to the resolution just with threat intelligence alone. If we look at the output from the analysis classifier, it shows that the probable process is Sality malware. For those of you not familiar, Sality is a file infector. However, like other file infectors, there may be false positive issues. How can we determine more definitively if this is malicious or if this is a false positive? In the output from the fused record, you can see the process name, in this case, Duo device health. There's the process hash, truncated to fit on the slide. We have the TLS fingerprint, and we can dig into that a little bit more in a bit. It also shows that AV didn't detect this sample. Analysis identified this as suspicious, which is why we're looking at it here. But the fingerprint isn't rare, so let's look into it more. So let me take a quick diversion to evangelize why Jupyter Notebooks can be so useful for this kind of work. And I'll give the acknowledgement to John Lambert, who was talking about this a number of years ago at the MITRE AttackCon in terms of how to use this in his workflow. So it's a great way to experiment one cell at a time. For any of us in the group who learned mathematics in university and grew up with Mathematica or MATLAB, this may be a familiar development model. And given that you're executing one cell at a time, it's much more forgiving for people who say, oh, is that function for a data frame? Is that a PySpark data frame, or is that a Pandas data frame? I can't keep it straight. It's also really great to be able to load your data once and then say, How can I ask different questions? Yes, you could do all of these things in regular Python and just run it and wait for the result, but kind of that iterative interaction gives you some opportunities to test things. So here we break the fingerprint into 3 different groups. On the first line, you can see that this is TLS 1.2, pretty standard. Looking at the second line, when we start digging into cipher suites, we can find some interesting things. On the third line, there's the set of extensions. If this really is duo device health, the TLS fingerprint should be the same as what we see for duo device health across the network. If we look at the TLS fingerprints for duo device health for a single day of our data, we see 23 unique fingerprints. Here we're showing 3 of the fingerprints with similar cipher suites. That's the beginning with the C02. Next to each of these, you can see the edit distance. This is how many characters you would need to add, delete, or change in that fingerprint to get to what we would see from the traffic here. The closest edit distance that we're showing here is 24 from the observed TLS fingerprint. So what does this mean? To us, when we see that the TLS fingerprint doesn't match, given the prevalence of the process on our network, it points to something suspicious. Let's look at the set of applications that have the fingerprint that we observed in the network data. So on the last slide, we started with the application name and looked at the fingerprints. And now if we start with the fingerprint and look at the application names, you can see what matches. Again, looking at a single day of data, there are 101 applications that match this fingerprint. Some of them you would most likely recognize. Word, Excel, Outlook, OneDrive, WebEx, WhatsApp, Acrobat, Creative Cloud, Firefox. So from this, what can we conclude? It appears that this is in fact not duo device health, but network traffic associated with common Windows network code. How can we explain this? Probably the file infector was using a common network library. So in this case, we can mark the event as a true positive and send it for remediation. Let's look at what we covered today and hopefully maybe some lessons learned. So there are a number of different ways in which this automated processing can go awry. So first, if the data ingested from your source feeds is of poor quality, then the output of your classifier is also going to be poor. This is the garbage in, garbage out problem. If you have IOCs that you're ingesting from third-party partners, it is important to either evaluate them or have a process for cleaning them up. The best case scenario is that your set of threat intel is going to be incomplete. Often it's much worse. In terms of malware samples, if all of the PCAP from your sandbox runs is labeled as malicious, then running benign software in your sandbox can reduce the efficacy of your classifier. And lastly, for those of you considering building a cluster like this, no matter how fast a compute cluster might be, data scientists are always going to want to squeeze one more run out. One more experiment, one more test, something else, right? So that's the tricky thing in terms of quantifying that in your build is going to be a little bit tough when you're going for budgeting. So sometimes we focus on all the things that can go wrong because that's what needs to be fixed. A lot of things can go well. There can be an end-to-end pipeline. This can start with a network tap, flow through an automated process, into your SIM, and then into your automated case tracking system. And that's what we're doing today. This is extremely scalable. Scaling the compute with Spark is relatively simple. For a smaller network, this could be as small as a few nodes. You can grow for a larger network. Additional compute can be easily added. Your model can also be rebuilt on a daily basis to update the classifier. The software on most networks is continuously changing. So whether it's a new version of TLS or a new browser version or a new application that you haven't seen before, that can easily be updated. I know that our time today has gone quickly, but let's recap. We talked about why logging DNS events on your network is so critical. Hopefully, the next time someone tells you that everything on the network is encrypted and you can't see anything, you can use this as a great example of what you can do with existing information. DNS data can definitively answer those CSO questions, and very quickly. We talked about different data sources that are inputs to our pipeline. Some of these data types you probably already have now. Lastly, we walked our way through an example of how to use this data to determine that something was in fact malicious. I want to thank everyone on the team. I'm just one person standing up here. I work with some amazingly talented people. This talk is the results of a lot of work from absolutely everyone on this list. Andrew and Blake are amazing data scientists. Brandon and David did most of the work writing the early versions of Mercury. Igor and Lucas are outstanding system administrators who kept everything running for us. Lucas was at Cisco, but has since moved on to AWS. Joey is an excellent analyst who made sure that all of our findings made it into cases, and those cases got resolved. Thank you, Joey. I really appreciate it. So thank you, everyone, for your attention today. If you are interested in testing out Mercury and to see what it can do for your environment, you can find it on our GitHub page at github.com/Cisco/Mercury.